Beep. Yes, let's motivate the whole riding my bike down the hill with a look at where we're headed next. So we just did what's called linear modeling, and that's when the data that's presented in front of you behaves in a linear form. In other words, you see data points, and there's a constant change, as Jen so expertly noted earlier with the pressure example. For every 10 feet drop in depth, we increase 0.433 in pressure. Don't write this stuff down. This is kind of a motivation as to why that's not enough. That's not enough, because not everything on Earth behaves linearly. Not everything on Earth behaves. Some things do. Some things are great. There's usually a linear relationship, for example, between the size of your hand and the size of your foot. I've seen all kinds of these kinds of neat little so cool. Hello. Light gremlin. So anyway, what I want to look at is something called a conic section. We mentioned this earlier with Matt's coffee cup. If you start with a cone and you chop it in various ways, you get different shapes. If you cut it right across the top, you get a circle. That's your frustum, which is left. If you remove the little cone from the top, you get a big frustum left at the bottom. If you tilt it a little bit, you get what's called an ellipse. If you tilt it far enough, but not too far, if you tilt it too far, you get what's called a hyperbola. But if you tilt it just far enough, you get a parabola. Now, you remember the word parabola from your previous math classes, I'm thinking. What does a parabola look like? Draw with your arms. Give me the parabola dance. Well, or this. That's what you pick. I mean, pick it a dance, I guess. Yeah. So parabola is ish like this. Parabola is ish is going to be this kind of a shape. So it's got this part at the bottom, which is called a what? Remember that? That's your vertex, which then branches up. Remember what these parts are called up here? The two branches? Does that ring a bell? It might not. Not everybody uses those terms. So you got a vertex, which is either a low point or a high point if you're going down. If you're going down, it's a high point. So it's called the extreme. Either extreme low or extreme high. And you get these two branches. Tell me about the branches as they go up. How do they go up? Good. I heard outward. I love that. I love that. They do. As they're going up, they're also going outward. Say that again.
No, I'm agreeing with you.
Oh, you're agreeing. Well, thank you. Hi. So, suppose I only drew one of them.
Exponential.
It looks, who said that? I love that. It looks exponential, Echo, but it behaves differently. We'll look at exponential modeling next time. Exponential grows at a different rate, in a different way. Thank you for that, though. We'll come back to that. I promise you, that's like next week. If I only give you one of the two branches, could you sketch the other one with relative accuracy?
Yeah.
Because what is a parabola? I just heard it. It's symmetrical. If you fold the one branch over, it folds on it. Exponentials don't do that, Echo. They don't do that. The general exponential does it. They have an explosion on one side and then a flattening on the other side. So that's what this parabola, if you can envision a cone that you then chop down like this, you can see the symmetry. It's a little harder on a 2D screen. So rather than focus on the conic section, I want to focus on what makes a parabola, and then we'll go out and take some measurements. So here's a parabolic shape, that blue. Remember how when Echo asked about the ellipses, we talked about the two foci? A parabola has one, not two, but one. It's got a focus. And when light beams or any other kind of energy beam come in and hit the parabola, they will bounce off and all head to the focus. This is really, really cool for your lives in a lot of ways. For example, how many of you have seen one of these? That's a parabolic antenna. Why would this be a good shape to use for collecting things like radio waves or television waves? Because that's a pretty wide open. You see where the focus is? Focus that thing out on the beams out there. Every signal coming in is bouncing off that screen and heading up into that focus, where it can then be transmitted inside and distributed. As opposed to it going all over creation, having to gather all that up and put it in one place, it's automatically heading to one place. Pretty rad. That's a pretty useful use. Here's an example of it. This might keep trying to turn the lights off. I don't know if you can tell what's going on there. It's a parabolic mirror. See what the guy's doing? Holding a piece of cardboard at the focus, and what's happening? It's burning the cardboard. All those light rays are coming down and heading into the same point. So each light ray is not going to catch a piece of paper on fire, which is 451 degrees Fahrenheit. But if you take all of those light rays and refract them back up into that one point, you get the sum of all of that Fahrenheit, if you will, all that intensity of the energy, and it actually is enough to set the fire going. If I remember correctly, yeah, this is how they lit the Olympic torch when it was most recently in Greece. They actually created a little parabolic mirror, and she doesn't look very happy about it. But she's down there holding that torch, and they got hot enough to light the torch from a parabolic mirror. Pretty rad, pretty rad. Please, Gabe.
There's a survival tip if you could have like a soda can.
Yeah.
And a piece of chocolate.
Yeah.
You flip the soda can upside down and rub the chocolate to polish the bottom
Oh,
of the Coke
interesting.
bottle, and then you could use that to reflect the sun rays
To one point.
fire. Yeah.
There was I did not know that the chocolate would polish that's pretty cool. How did that work? Chocolate polishes
I
aluminum.
have no idea.
That's pretty rad. There was a short-lived show called like Survivor Island, where it was like Survivor, but it had like real people on it, and they actually had to do things other than just sit around and make out. So they put like scientists on this island, and they went around and picked up trash that had washed up on the beach and built things. And one of them actually built a parabolic mirror out of basically tin foil that had washed up, and they smoothed it and kind of bent it, and they kept working at it until they could cook food off of an oven they created from trash on the beach. This show didn't last. I can't imagine why. People weren't half naked all the time. But nonetheless, same kind of cool tricks, though. Same thing. Tell me your name again, too.
Scott.
Scott, yes, go
I
ahead.
actually built one of those. I rented an apartment that was upstairs, and I got free internet from downstairs. And
By picking up their signals?
well, what I actually did is I was like, how do you boost it? How do you boost it? And there's a website, and what you do is you actually build one, and it's made out of a cutout, and you have foil behind it. And it works so, I mean, it went from like 1 signal to like 5. It was actually stealing 70% of their internet. It wasn't allowing
I love mathematics! Especially when it allows you to go on the radar! You hearing this, YouTube world? You learned it here! Where's the microphone? That's okay, the camera's picking it up. I'll just make sure I say it nice and loud. It's amazing. It seems amazing, but it's math. I mean, that's the thing. This is what bums me out. Math 105 should not be the first time you learn this stuff. You should learn this stuff in like geometry class in high school. You shouldn't be factoring binomials. You should be learning about how to make parabolic mirrors and stuff. Totally. Maybe not stealing your neighbor's signals, but here's the thing. But here's the thing. The signal's in the air. Is it regulated? Maybe it probably is. I'm sure some governmental agency has their thumb in it. But like, if it's in the air, it's like, oh, I got some. I mean, it's out there. It's like you're not regulating the air I'm breathing. Why not pull it? Anyway. Here's another use. A microphone with a parabolic mirror. You've seen these at NFL games. That's how they can point. There was a great video somebody just showed me. It was a bunch of NFL clips where they had put other speech over the, I forget what it's called. It's funny. YouTube it. It's hilarious. It's something like worst voiceovers in the NFL. And what happens is they can point the microphone down at the field from hundreds of feet away and pick up very clearly what's being said because of the focus idea. But somebody had done crazy voiceovers over the players' mouths, and it's so funny what they have them saying. YouTube, it's pretty funny. Anyway, you can also go the other way. So everything I just showed you was signal coming into the parabola and then reflecting into the focus. You can also start at the focus, send signal out from the focus, hit the parabolic mirror, and then send the signal out, like your car headlight. Take a look at your car headlights sometime, especially one of the newer LED model headlights, but even the halogen lights. The technology in those is all about the mirror. It's all about the mirror, because the mirror is what sends the light out in a straight beam. If you've got a very weak beam, it could be your mirror is either damaged or dirty, in which case the light isn't coming out in these very strong parallel waves. So headlights are like that. This is the bike headlight I commute with. It's 1,000 lumens. It blinds people. It's so bright. I've actually had people tell me it's brighter than both of their car headlights together. One of my friends actually duct taped it to his hood and went down the street with it just on the hood. He's like, dude, it's actually brighter than my headlights. And it is that bright because I don't want cars hitting me. And I want to see where I'm going. So, this is, yeah, that's math. You don't care about that. This is, as you know, the shape of those cables where applied to tension is another example of a parabola. It's another example of a parabola. Now, I am going to back up to this beautiful little picture here, because this is actually the mathematics of what's going on in the bridge. The distance, there's your focus, that point F up there. See that line L at the back? That's called a directrix. The way you would draw a parabola, and I for years have thought about doing this with my 105 classes, you draw a directrix, you draw a focus, and you draw the set of all points that are equidistant from here to here. These two distances are the same. That's the definition of what makes a parabola a parabola. So the set of all points that are equidistant from both here and here is actually the parabola. You can kind of see that in things like the Golden Gate Bridge, or from my hometown of Wilmington, Delaware, the longest twin-span suspension bridge in the world, the Delaware Memorial Bridge. You can actually kind of see this whole parabolic nature, and I love the drop-in of the vertical suspensions. When you don't have the drop-in pulling down, it's something called a catenary, but as soon as you apply pressure to it, it becomes parabolic, which is totally rad, totally rad. So these are some kind of structural elements of the parabolic uses. What I want to do next, now that I can't turn the lights on, oh, there we go, is I want to show you another use of it, but it's going to require us to get data. So what I'm going to do is turn this off.